Welcome to another video for Stat 420. In this video, we're going to again be doing some simulation in R, but this time we're going to be doing it in the context of simple linear regression. So what we're going to do is define kind of a relationship that might exist between two variables by defining some parameters here. So like what the slope and the intercept would be for this relationship, as well as the variance that exists in this relationship. Then we're going to randomly sample some possible data points that we might get if we have two variables with this set relationship, and what that data could look like. And then we're going to kind of compare it to the model parameters to see how close our linear model kind of approximates what that relationship really is. So first I'm going to set an intercept and a slope for this relationship. So I'm going to do an intercept of 2, and I'm going to do a slope of 0.5. I also need sigma, so I need or some kind of measure to represent the variability in this relationship. So I don't want two variables that are perfectly correlated. I want two variables that have some relationship, but also have some variability as well, meaning that the predictor variable does not tell me everything about the response. It just gives me some additional insight here into what might be going on in the response, but that obviously other things are going to be involved here too, that there are other variables that also relate to the response variable as well and explain that relationship. So I'm going to set sigma here to just 1. And then one other thing that I will mention here or define here is just how many samples I'm going to take. So I'm going to take 50 data points, 50 XY pairs that I'm going to kind of randomly sample from this multivariate distribution. Next, I'm going to predefine some random noise. I could do this a couple ways, but what I'll do here is I'll follow the book and create some epsilons ahead of time. So epsilon is going to be the residual for each data point. And we know that if our linear model assumptions are met, then my residuals are independent of one another, and we know that they're distributed with a mean of 0 and a standard deviation of whatever the standard deviation for the residuals is, so for some standard deviation. So I'm going to do R norm. I'm going to sample n data points, or n epsilons in this case. The mean of this distribution should be 0, meaning it should be centered around the line, which we'll see. And the standard deviation is going to be what I set sigma to be there. Next, I'm going to also randomly sample some x values to start with. So basically, I'm going to have a set of x values. Then I'm going to plug those into this equation with these epsilons to kind of simulate some possible y values that I could given this multivariate relationship. So what I'm going to do here is set x vals equal to r unif. In other words, kind of randomly sampling from a uniform distribution. I'm going to randomly sample 50 x values, or n equals n to be consistent there. And I'm going to go ahead and do 20 to 40 as my range. It doesn't really matter that much, but I will randomly sample from the range 20 to 40 for my x variable. I'm going to go ahead and run everything that I have so far here. And then next, I'm ready to randomly generate some y values that I could reasonably get, given that these are the x values that I have, and given that this is the relationship that I have between these two variables. So y vals is going to be equal to my intercept plus my slope times my x vals plus this random noise epsilon. Right, so it's not a perfect relationship. There is an underlying relationship with some other variability as well mixed in. So I can simulate that, and now I can kind of take a look at what I have here. So I'm going to go ahead and just plot this real quick as well. So I'm going to do plot x, y. I'll fill in my points because I don't really like the open circles, and I'll go ahead and color it purple. So we can see, oops, let's see, what did I miss here? X, Y, PCH equals 20, object X not found. Oh, you know what? It's X vals and Y vals. There we go. All right, so we can kind of see, right, that there is some kind of relationship here, but obviously there is some other variability as well. So there's not a perfect relationship, but there is some relationship with some additional unexplained variance in y that cannot be fully explained by knowing x. All right, so let's go ahead and also define a model here. So I'm going to just call it model equals linear model of x vals, or actually I should do y vals tilde x vals. In this case, there's no data from that they're situated in, so I'm just going to run this as it is. And then I can just run the model here. And you'll notice that my intercept and slope, my intercept has a little bit of distance. It should be around 2, so there's not quite as much accuracy there, whereas the slope is actually pretty good there at 0.5 or 0.5051. Although I guess proportionally, if I think about the scale of each of these, I guess they're about proportionally similarly off there. But again, this is just kind of a reminder here that when we run a model with a random sample of data, these coefficients are estimates of what the true parameters are. So even though in this case I do happen to know what the parameters are that these were simulated from, when I do this in real life, I won't know this. All I'm going to know is this part. And so I just have to keep in mind that what I'm getting from my models here are estimates of the parameters. They're going to have a little bit of error in them. I also know that the larger the sample I take, in general, the more accurate my estimates are going to be. Again, they're still not going to be perfectly correct, but they should be a little bit closer on average. Or actually, whoa, so I actually had a pretty bad set there. So even though I sampled more, I actually got a little bit more error in my intercept. So I'm actually going to do that again out of curiosity. So again, on average, I should get more accurate values. And in this case, well, I'm not doing so hot, honestly. So let me actually go back to 50 out of curiosity. So maybe I just got a really good batch with that first 50. So if I go back to 50, let's see how much error I have. Yeah, and so this one's actually quite a bit off on the intercept and several scales off in the slope there. So I probably just got a really good batch of 50 on the first one. But in general, obviously, the more data I have, the more accurate I'm typically going to be with my model coefficients. But again, I could still happen to just be very accurate with a small sample, but it won't be as reliably accurate with a small sample. All right. So one other thing that we're going to do is just practice storing this simulation as a function. Not because this particular exercise is necessarily important, but because in general, when we're working for a company or we're working in research, there might be some kind of computation that we do a lot that we might want to save under a function so that every time we have a new set of data or a new situation, we can just call on that function instead of trying to write basically everything that I did again each time uniquely. So this is a good exercise for us to try, is just saving this as a function. I'd encourage you to think about it on your own first, but I'll go ahead and do this here. And I'm going to do it slightly differently than the book as well, just for kind of sake of discussion here, that it's really up to what I want in the function versus there being a correct way to do this. So I'm going to name my function sim SLR. It's a function, and I'm going to do these 4 parameters. I'm going to do sample size as one of my parameters. So I'm going to do n. I'm also going to do, again, beta naught, beta 1, and sigma. Now, obviously, this is a choice, so I think this is a departure from the book, if I remember correctly. But I'm going to go ahead and set one of my inputs as my sample size. Okay. So inside my function, I again need to simulate x. So I'm going to do x is uniformly distributed. Now, again, this is another choice, right? So maybe I already have some x values, so I don't need to simulate x ahead of time. But for sake of this function, I'll go ahead and do it. But there's kind of another discussion point of, it depends on what you want your function to do. If you already have x values, which may be the case, then you wouldn't need to simulate them randomly inside your function. Instead, you would just kind of add it as another parameter that you're inputting already. But for sake of this example, I'll go ahead and throw it in the function. I'll go ahead and do 0 to 100. Why not? There's not really any right answer here. I also need to randomly sample some epsilons. Oops, epsilon equals, and again, this is going to be our norm with n, mean equals 0, SD equals sigma. I'm going to now simulate some new y values. So y is going to be beta naught plus beta 1 times x plus epsilon. And lastly, I'm going to store my x and y together in a data frame. So that way, what's outputted by this function is going to be what I list last here, and that's going to be a data frame of my x and y values. So let's run this. Let's make sure that I did this correctly. It's very possible that I forget something here and there. Okay, so now let's go ahead and run this function where we fill in some parameter values, and we're going to save this function output to a data name. So I'm going to call it simData, and it's going to be this function result. So sim SLR, let's set n equals to 200, because why not? Beta naught, let's do negative 50. And beta 1, let's do 2 or 3. And then finally sigma, let's do a lot of variability. Let's pump this up to about 15, just for see what happens. Okay, so let's run this, see if I did it correctly, and I do get some data here. Let's go ahead and plot this data and see what it looks like. So I'm going to do plot of y tilde x. My data is coming from simData. So now that I have my data saved in a data frame, I can't just do x comma y because x and y don't exist as defined vectors. They exist inside a data structure. So I'm going to do this. I'll add some plot features here as well. So let's go ahead and change the plot type to type 20. So these are filled in dots. Let's go ahead and keep the color black. And I guess that's all I need to do first. I'm going to go ahead and add a grid as well. And let's go ahead and add a best fit line. So my best fit line, I can either define from my model output, or I can actually save a model here and just plug that in, which is probably going to be easier. So let me do sim model equals a linear model of sim, oops, it's going to be y tilde x data equals sim data. And let's go ahead and add an AB line where my model is going to be sim model. I'll do a line width of 2, and let's make the color equal red. All right. So it looks like my data doesn't have a whole lot of variability. So even though I thought I was adding a whole lot of variability, I guess it wasn't as much as I thought. So just for fun, let's go ahead and up that to 40 and notice how that changes the plot. And we should notice, yeah, we definitely have some more variability. Let's go ahead and even do it some more here and just see, again, what happens if I do like 75 now. So we should get even more variability again, and there we go. So again, this relationship, we can still see something there, but it is getting more clouded as the amount of unexplained variability is going up in this model. And let's go ahead and also take a look at our model. Let's go ahead for a change of pace. Let's do a summary here. So instead of just getting the coefficients, let's get a little bit more here, including r squared. So our intercept is estimated to be minus 54. Our slope is about 3.229. So definitely, you know, in the ballpark, but you know, a little bit of error there. Our r squared at this point is still about 66%. So we're still explaining 66% of the variability in y by knowing x. But again, as we increase the sigma value, that r squared would keep going down to signal that there is more variability in this data that is not being directly explained by knowing x. Okay, so I think that's about everything I wanted to show you. I'm trying to think if there's anything else that I wanted to do. Oh, you know, what I wanted to do is do a side-by-side of my fitted line, so using the data compared to using the actual parameters. So instead of plugging in sim model, I'm going to actually plug in my intercept would be, let's see, -50, and the true slope would be 3. I'm going to make this line width as well, too. I'm going to make this one a line type equals 2, which I believe would be a dashed line. I'm going to keep this one black, though. So let's take a look at that difference. So we can see that these lines are pretty similar. Again, if I want to increase the sigma even more to like 150, we'd probably see a little bit more departure, most likely, between these two. You know what I need to do? I'm going to have to put, nope, no, it's already defined there. But the more variability we add, in general, the more departure we might begin to see. Also, if we decrease the sample size, it would also increase the likelihood that we see these lines diverge a little bit more. So I'll go ahead and down this to about 40, just so we can kind of see that difference as well. Oh, well, we got really lucky on that one. Let me do, well, actually, I'll just do it again with the same data set or same sample size. There we go. So here's when we see a little bit more departure. So the smaller the sample size, the more likely we are to see a little bit more discrepancy between our model estimate and the actual parameters there.